everyone. It's weird not to see all of your faces, but anyway, we are starting to get used to it, I guess. I will talk about exoplanets and habitability. So I'm Emeline Bolmont, I'm a professor at the University of Geneva. And working on the thematics of climate and habitability. In this course, I will try to do something with you, and in particular, I will at some point ask you questions, and so if you flash this QR code, or if you type in this address, then you will be able to see a question, and you will be able to answer it, and hopefully most of you are going to be able to answer the question, and then I will show you what everyone answered. So if you take some time to flash this code or write the email address, the address, and anyway, when I have a question, I will put this symbol again, so that if you don't have the opportunity to do so right now, you will have some other opportunities. Okay. So let's begin. So one of the big motivation of the field of exoplanets, obviously, and that's why we are here today and this week, is there life out there in the universe, right? Can we find planets with life on it? And so this question obviously was a question that humanity asked itself for since the beginnings of times, I guess. And so right now we are in an era where we start to be able to bring maybe a few elements of answer. I'm talking only on the astronomy point of view. And so I will show you during this talk that we have detected planets in this famous habitable zone. So we will see together how we define this habitable zone. And we will see that in this habitable zone, we actually have some planets that are going to be probed in the future, in the sense that we are going to be able to observe their atmosphere and potentially be able to say which chemical elements are composing this atmosphere. Okay, I see that I need to put the poll link in the chat. So let me check if I can do it. Okay. Let me write it down because for some reason I can't copy paste. So yeah, that's the idea of the talk of today. And I will begin just after writing that down. Up. I think that's it. Send. Okay. I guess you should be able to see it. Anyway, let me continue.
All right. Somebody wrote it on the discussion already.
Perfect. Okay.
Thank you, Olivier.
Thank you. All right. Okay. So the question that is interesting for us today is how do we define habitability? So I will go through a list of various definitions depending on who you are, what you are working on. You might be have more affinity with one or the other. So the first definition of habitability is a habitable body, like a planet or a moon, is a body that meets all the necessary conditions for the emergence and the development of life. Okay, so that's a good starting point, but life is a very generic term, right? And the important thing here is that we only have one point of measurement of life, which is life on Earth. So let's already change our definition to a slightly different one, where this time we focus on life as we know it on Earth. And if we focus on the life that we know it, we can actually go a bit further, because we know actually the building blocks and some of the conditions we think are required for life to be there. So the first condition, of course, is to have the building blocks. So life is based on carbons and over elements like hydrogen, oxygen, nitrogen, phosphorus, and sulfur. So you need these building blocks available to you. You need liquid water. So this, because water is a good solvent, it helps to do the chemistry reactions that you need to have life appearing, let's say. On Earth, we know that this ocean is on the surface, on a rocky surface, and you have continents, etc. So you need a surface, and of course you need a source of energy. So it can be energy coming from the sun, or it can be geothermal energy, for instance. And so that's the building blocks of life, let's say, as we know it. So let me just quickly mention a bit about the energy part. So on Earth, we have the two types of energy. Actually, we have the geothermal and the energy coming from the sun. But I just wanted to mention here the difference maybe in orders of magnitude between these two sources of energy. So if you look at on the left, so the geothermal heat flux, so you can see that it's concentrated along the ridges, for instance, here in the middle of the Atlantic. And the flux is given in a milliwatt per meter square. And so you see at maximum, you have this range of flux for the geothermal energy. On the other side, you have the energy that we receive from the sun. This time it's a flux in watt per meter square. So you can see already that we are a few orders of magnitude above the geothermal heat flux. And so here you have the map. So it shows you that the poles receive very little energy, and obviously the equatorial region receives more. So for us, we are dominated by the energy coming from the star. And keep in mind this geothermal flux thing, because at the end of the presentation, I will show you a bit about that for exoplanets, for a particular system of exoplanets. All right. So this leads us to a third definition of habitability. And so a habitable planet or body, let's say, is a body that has a surface, that has liquid water, that has the good chemical elements to form organic molecules, and a source of energy. So for instance, photons or geothermal energy. Okay, and actually the thing is that liquid water is very likely to be the most limiting element in the habitability of planets. So it's easy to find carbon, because there is a lot of carbon in the universe, let's say, or less than hydrogen, but there is carbon and it's available to us. A source of energy, well, if you have a sun, you're going to have some kind of source of energy, and you can also focus on planets which are rocky. This way you have a surface. But for the liquid water, it's a bit more difficult. And so if we take the example of our solar system, the only body that has surface liquid water is the Earth. In the solar system, we know of a few bodies that have water, but it's usually subsurface oceans. And so right now we have the first question coming up. So you can use the link that was shared before, or you can flash the QR code as you prefer. And you should see now a question appearing on your screen. And so the question is, in your opinion, which body of the solar system hosts the most water? So maybe you've seen that today, I don't know. But let's see what you answer. So I will let you answer a bit, and then I will show you what you voted for. So I can see people voting, and things are moving around. Okay, it's getting kind of stable. So I'm going to show you what you've answered. Okay. So now you should see the result of this little poll I did. So some of you answered Titan. Very good that nobody answered Venus. Okay, so Europa has a lot of votes. The Earth, not too much. Okay, that's nice. All right. Actually, the body that has the most water is not Europa. It's actually Ganymede. So let me go on with the presentation, and I will show you okay, so here is a census basically of the water that's available on different bodies of the solar system. And so Europa is just next to Earth, actually. You can see that okay, so here you have the sizes of the different bodies. And the blue ball actually corresponds to the size that, for instance, all the water on Earth would have if you put it into a bowl. And so you can see that the Earth actually has a very small amount of water compared to its size. And for us, it's completely different from our experience, because when you see typical pictures of the Earth from the space, you have the impression that it's completely covered with oceans and that there is a lot of water. But actually, if you compare it with the other bodies of the solar system, it's not too much. And so Europa is here, it's at 18% of water in volume. And actually, if you go to the right of this diagram, you have the body that has the most water, and it's Ganymede, actually. But what's the common point between all these bodies that are rich in water? And that's a big problem, because actually this water is not on the surface, obviously, it's a subsurface ocean. And so if you want to look for life and you want to go where the water is liquid, for these bodies, you're going to have to go through actually this ice layer, which is on top of the ocean. And so it's actually difficult to explore in situ, because it would mean, to not only like send a probe, but the probe will have to drill into this ice layer, and this ice layer in some cases can be very deep. But you have some cases where you have like cracks and through this ice layer, and you can have material going into the atmosphere. So plumes, like for instance for Enceladus. Enceladus actually has plumes which could be probed without drilling, but it's tricky anyway. And so it's difficult to explore in situ, and it's even more difficult if you want to explore it remotely. So from Earth, trying to see if there is life in these subsurface oceans, it's really very difficult. And so for the exoplanets, obviously we are not as close as these bodies, so we are completely dependent on remote observations. So for instance, for these bodies, those are not the best candidates for us, because the water is not on the surface, it's hidden. And so basically we are looking for planets like that with surface liquid water like the Earth. And so we have to find somehow the surface liquid water. So this brings us to the fourth definition actually of habitability, and it's actually this one that us exoplanet scientists are using. So a habitable planet is a planet that has surface liquid water. And so from this question in the beginning, are we alone in the universe? Then we go to a much more down-to-earth question. Can we find planets with surface liquid water? And to answer this question, the community has invented a concept, which is the habitable zone. So the habitable zone, we will see exactly how it's defined, but as a first zeroth order approximation. If the planet is too close to the sun, basically it's going to be too hot, and the water is going to be gaseous in the atmosphere, and so it won't be liquid on the surface. If you're too far away, then this time the water is going to be icy on the surface. And you have a sweet spot in between, where a planet with the right conditions can sustain liquid water, and this is this habitable zone. And so we are going to see together now how exactly do we define the inner edge of this habitable zone and the outer edge of this habitable zone. Okay, so let's begin with the inner edge of the habitable zone. So this edge, there are basically two definitions to define it. The first one is called the runaway greenhouse limit, and so it was something that was proposed by Casting in the 90s. So what's the principle of this limit? So let's assume that you take the Earth and you put it closer and closer to the star. So you increase its temperature. If you increase the temperature of the planet, you're going to increase the evaporation of its ocean. So it means that you will have slightly more water in the atmosphere of your planet. And so because water is actually a very efficient greenhouse gas, you will increase the greenhouse effect on your planet. And increasing the greenhouse effect is going to lead to an increase of temperature. So in the end, you have this positive destabilizing feedback loop happening where you increase the temperature, and in the end, it increases the temperature, and it's going to have a runaway. This is the runaway. So before going a bit more into the details of this runaway limits, let me just do a small parenthesis on some terms that I'm going to be using later. And so this concerns what we call the radiative energy balance of a planet. So let's assume that our planet is solely being heated by the light coming from the star. So we have some incoming stellar radiation that is going to heat up our planet. This light coming from the star, there is two things that is going to happen to it. You're going to have some of its light that is going to be absorbed by the planet, and some of it that is going to be reflected back into space. And so this process is actually quantified with a parameter which is called the albedo of the planet. So for instance, if you have an albedo of 1, it means that the planet is going to reflect all the light it's receiving. And if the albedo is 0, in contrary, the planet is going to absorb all the radiation and reflect nothing back into space. And so for a star like the sun, this radiation basically it's in the visible wavelength range. And so this light is going to heat up the atmosphere, it's going to heat up the surface. And as you know, if you heat up a body, it's going to emit a thermal radiation, so this time in infrared. And so you have a thermal radiation that is going to allow the planet to cool down, basically. And so if you have if the planet is in equilibrium, then you have a perfect equality between what the planet absorbs, so what it uses to heat itself up, and the thermal radiation, so what the quantity that allows it to cool down. So you heat up as much as you cool down, and so you have an equilibrium and a constant temperature. All right. So if we take back our example of the Earth and put it in closer to the sun, at first what happens is that, okay, you're going to receive more incoming stellar radiation, so you're going to absorb a bit more. And so the thermal radiation is going to increase a bit in order to retain this equilibrium. Okay. All right, so let's see what happens on this plot here. So we have the surface temperature and we have this thermal emission, so the one that allows the planet to cool down. So at first we begin with a planet which is habitable, so like good temperate conditions on the surface. And if we bring the planet closer to the sun, as I said, you're going to increase the temperature and also increase the thermal emissions to allow the planet to cool down and remain at equilibrium. But actually, at some point, what's going to happen is that you're going to have so much water in your atmosphere, and especially in the bottom of the atmosphere, that you're going to become opaque to the thermal radiation. So basically, just like if you had a blanket over your surface, and the heat coming from the surface is not going to be able to get out. And so it means that the planet can't cool down. So it means that the thermal emission is going to reach a limit. And from there, actually, what happens is that you're out of equilibrium. The temperature is going to increase dramatically. And you're going to regain an equilibrium where the planet is so hot that it's no longer emitting in the infrared, but it's emitting invisible light. And so once it starts emitting invisible light, then you regain an equilibrium and you regain this increase of surface temperature with thermal emission. And so this transition from a temperate climate to infernal state, because here actually at the top the temperatures are like thousands of kelvins. So you really have a really hot planet. So all the oceans are vaporized, and you have like a huge atmosphere of mainly dominated by water. And so this limit actually tells you where the inner edge of the habitable zone is in this runaway greenhouse scenario. So here, for instance, is a real plot, so not only a schematic curve. So here, actually, this plot was obtained with a 1D climate model. So actually, you model one column of your planet, and you look at the results. And so you can see Earth is here. So Earth is actually not very far from this runaway greenhouse limit. If you bring Earth a bit closer, then it could enter this catastrophic runaway phenomenon. All right, then I told you that there were two definitions of the inner edge of the habitable zone. So that was the first one. The second one is called the moist greenhouse limit. So so what happens is that, okay, when all the water, when the water goes into the atmosphere and the planet begins to be hotter and hotter, actually what happens is that the atmosphere is going to extend a bit, and it's going to be hot, and so you're going to find some water in the upper parts of the atmosphere. And here the key point is that a star is an active object. It's going to emit high energy radiations, and in particular X-rays and extreme ultraviolet radiations. And this radiation is going to impact actually the water that is in the upper atmosphere. And so in particular, the far ultraviolet radiations are going to break the water molecules. It's called photolysis. And the X-UV radiation, actually the impact of that is going to be to increase the temperature of this upper part of the atmosphere and to drive the escape of the hydrogen and oxygen atoms. Now, because the hydrogen is much lighter than oxygen, hydrogen is going to escape a bit faster than oxygen. And this way, a planet can lose its water. And so if you wait long enough, actually, the planet can lose all of its water with this mechanism. And so if you lose all your water, then of course you won't be habitable either in our definition. Okay, so we have these two limits. It's not clear actually which mechanism is the fastest, and possibly it also depends on the star, because if the star is more active, maybe it's going to favor the moist greenhouse limit. If the star is not very active, maybe it's going to be more of the runaway greenhouse limit. But so it's just for you to know that these two definitions exist. And if you do a 1D model like the one I showed you earlier, you can actually give a distance of the inner edge of the habitable zone. And so, for instance, for the runaway greenhouse is about 0.84 AU. For the moist greenhouse is 0.95 AU. All right, so now let's move on to the outer edge of the habitable zone. So the outer edge, you also have a feedback loop that is happening, but it's a bit different, obviously, than the one on the inner side. So here what's happening is a runaway glaciation mechanism. So let's now, instead of bringing the Earth closer to the sun, let's bring it a bit farther and farther away. So if you do that, the temperature is going to decrease. if you decrease the temperature, it means that you're going to have more ice, more snow at the surface of your planet. And because ice, snow, and snow are very reflective, you're going to increase the albedo of the planet. So the reflection power of your planet. And so if you increase the albedo, it means that the incoming stellar radiation that the planet receives is mostly going to bounce back into space. And so you have less absorbed radiation. And so you're going to have less energy. And so the temperature are going to decrease. So this time again, you have a positive destabilizing feedback loop that occurs. So now to find the outer edge of the habitable zone, you have to see how you can do to try to counteract a bit this kind of feedback. And one way to do it is to invoke greenhouse gases. So if you add greenhouse gases into your atmosphere, you're going to heat up your planet, and so you might be able to fight back against this feedback loop. And actually, that's how we do to find the outer edge of the habitable zone. It's called the maximum greenhouse limit. So the maximum amount of greenhouse gases that you can put on a planet that allows it to retain these habitable conditions at the surface. So usually okay, so there are several greenhouse gases that we can invoke that could help to delay this freezing over of the planet. So obviously there is the CO2. You also have the water vapor, as we've seen for the inner edge. It's a powerful greenhouse gas. And you can also invoke hydrogen or methane and ammonia. In most cases, the outer edge of the habitable zone is actually computed with CO2 because it's an efficient gas to warm up an atmosphere. And also it's very common in the solar system planets. And so but the trick is that you can't add an infinite quantity of CO2 in the hope that it's going to heat up your planet even if you put it very far away. Actually, there is a problem, is that if you add too much CO2 at some point, you're going to have Rayleigh scattering, meaning that the CO2 in your atmosphere is going to basically reflect the light coming from the star, and the light is not going to go deeper in the atmosphere and heat up the planet. And actually, you can also compute that, and it was shown that if you add more than 8 bar of CO2 in an Earth-like planet, for instance, then the planet is no longer going to be heated through this greenhouse effect, but it's going to cool down because Rayleigh scattering basically scatters back, the incoming stellar radiation back into space. And so this allows you to fix actually the outer edge of the habitable zone, because if you didn't have this Rayleigh scattering limit, let's say, you could imagine if you put like a ton of greenhouse gases, you could imagine to have a planet, a habitable planet even farther away. All right. So if you calculate, with this kind of 1D model that I mentioned before, you could find that this outer edge of the habitable zone for a cloudless pure CO2 atmosphere is about 1.67 AU. All right, so this gives you what we call the classical habitable zone. So when you hear, oh, we have detected a planet in the habitable zone, that's what it means. It means that it's in between these two edges. But you can see that these edges also depend a lot on the kind of assumptions that you make on the atmospheres that the planet has. So being in the habitable zone is not also a guarantee that the planet is going to have surface liquid water. That's also very important to remember. Before moving on, I just wanted to mention also the fact that habitability, so the habitability of planets have been also classified in 4 classes. And I would just like to mention that because it also brings back the question of the icy moons of the solar system. So the first class of habitability is class 1. surprisingly. And so class 1 is actually a planet like the Earth, which has a surface liquid water, and so everything is fine. Class 2 is a planet that was habitable in the past, but today is no longer habitable, can no longer sustain liquid water. So a famous example of that is Mars. So we know that Mars was habitable in the past because we have geological evidence on the surface of Mars that there were rivers flowing, etc., etc. Another planet that is often proposed in this class is Venus. Some people think that Venus could have been habitable in the past, so when the sun was slightly fainter. So yeah, these two planets would then belong to this class 2 of habitability. Then class 3 is basically an icy moon like Europa, so where you have a rocky core. On top of it, you have an ocean, and on top of the ocean, you have an ice layer. And so here, you no longer have surface liquid water like we have seen before. But here, what's important is that the water is in contact with the rocky part of the planet. So if you remember what we've mentioned on habitability in the beginning, so we need, a source of energy. We need the surface, liquid water, and nutrients like carbon, etc. Here, it's interesting because the water is in contact with the minerals, which is good actually. Because class 4 actually is kind of similar to this one, but this time you have a nice layer that isolates the liquid water from the rocky core. So here you will have an ocean that is not would have some trouble, let's say, to find carbon, a lot of carbon species. So you can imagine that here you could have some ice convection in the ice. So you can also imagine meteorites that could break through the ice layer here, but it's not particularly easy. And so this class 4 basically it's Ganymede and Callisto, for instance. And so in the domain of exoplanets, these things are basically impossible. We can't expect one day to find life around this kind of planets because the ocean is completely disconnected from the atmosphere, and it's the atmosphere that we are trying to observe. Class 2 is going to be hard because you have a planet, so you would have to find somehow evidence that before it could have had some water, which could be possible, but I guess it should be hard. And so class 1 is basically the class of planets that we are interested in exoplanet community. All right, so in this habitable zone, as I said in the very beginning of the talk, we have found planets. And so right now we have the second question I have for you, which is how many planets do you think we have observed in the habitable zone? So if you go to the same space as before, now you should have another question that is displayed, where I'm asking you to vote for a number of planets in the habitable zone in your opinion. Okay, some people are starting to answer. I'm going to show you because it's fun to see the thing happening in real time. Okay, so we have a big dichotomy. There are 32% which are, let's say, not very optimistic, and 16% who are very optimistic. Okay, I guess the numbers are not evolving too much now. Oh, the poll is full. Okay, that's a good excuse. Okay. All right, so actually only 4% of you got it right. Actually, it's actually we have found more than 200 planets in the habitable zone. So let me show you the real number right now. So here it's dating from June 3rd, so a few days ago. So here you have a histogram showing you the number of planets discovered per year. So for instance, okay, the first planet should be in 1995, but I guess it's classified in 1996 anyway. And so if you look at, okay, so the color code is where the planet is with respect to the habitable zone. So you see that it's dominated by the color red, which are planets which are closer in than the habitable zone. And this is just due to observational biases that we have, because it's much easier to detect the planets that are closer in. The planets in green actually spend some time in the habitable zone, and in blue outside, of the habitable zone. And so if you add up the numbers in green over there, and then you would have 204 planets. But the important thing here is that in these 2004 planets, actually the majority of them are big gaseous planets like Jupiter. So if you think back about our definition of habitability, what we needed is a surface. So if you have a big planet like Jupiter, you're not going to have a surface. So that does not classify as an interesting habitable planet for us. So basically what we want to look at is that in these 204 planets, which ones are small so that they can be rocky, so that they can have a surface. And if you do this exercise, actually, you find much less than these 204 planets. And I would like to mention a few of these systems that are interesting. And among these systems, I will mainly focus on two. So for instance, you have Kepler 186f, which was a rocky planet that was discovered by the American satellite Kepler. It's orbiting a star which is about 50% the mass of the sun, and it's the fifth star of a multiple planet system. Then you have LHS 1140b, which was also a planet that was detected orbiting in the habitable zone of its star. I think the mass of this one is a bit lower than that. And the two systems are actually I'm going to talk about a lot today. The first one is Proxima. So Proxima b, so Proxima Centauri first is very interesting because it's the star which is the closest to our solar system. And around this star, we have discovered a small planet. So it was discovered with the radial velocity technique. So actually, we only have the minimal mass of this planet. But it's a bit more than one Earth mass, and so it should be rocky. But it's not impossible that it's not rocky. But we believe that it should be rocky. And so this planet is actually in the habitable zone of Proxima Centauri. And this time, the star is actually has a mass of about 12% the mass of the sun. So a star which is much smaller than the sun. And finally, one of the most interesting systems that we have to play with nowadays is TRAPPIST-1. So TRAPPIST-1 has at least 7 planets. 3 of them are in this classical habitable zone that we defined earlier. And the star is about 10% the mass of the sun. So a very, very low mass star. And actually, most of these rocky habitable zone planets have been discovered around very low mass stars. So there are several reasons for that. The first one is just a geometric argument saying that actually it's much easier to detect a planet around a small star than around a large star. So for instance, if you take an Earth-like planet and you put it around the sun, I hope you can see the point here. But you can imagine that the transit depth that is going to have, I mean, the impact the planet will have on the luminosity of what you observe when the planet passes in front of the star is going to be very, very, very small. So if you take the transit curve of that object, you would have a very shallow transit. So it's very challenging to observe. If you put the planet around Kepler 186, for instance, it's slightly easier. So you will have a slightly deeper transit depth. And if you put it around TRAPPIST-1, this time you can see that the transit depth is going to be much higher. And this is because the transit depth scales as the ratio of the radius of the planet over the radius of the star square. So yeah, it's the bias is good for the small stars. Another also argument that makes it easier to detect these planets is that the orbital period of a planet like this around TRAPPIST-1 is much smaller than the orbital period of an Earth around the Sun. So, for instance, this very shallow transit, you will have to wait like 1 year to observe it again. But here around TRAPPIST-1, every few days or so, you will have a transit. So it's also much easier in that sense because you have a lot more opportunities to catch this transit from happening. All right, another argument for these cool stars, or M dwarfs we call them, is that these stars are actually very numerous around us. So here it's just a representation of the number of stars of different categories that are, I think, in a 10 parsec radius around the solar system. And so the sun is actually a G-type star, so it falls into this blue category. And actually, you can see that these low mass stars are representing the most common stars are these low mass stars. So they are very common. And last but not least, so we have seen that there is a lot of these stars, that the planets are easy to detect, but the most nice argument to look for planets around these very low mass stars is actually that these planets in the habitable zone of these low mass stars are the only habitable zone planets which we will be able to probe in the near future. And so by probing, I mean we are going to be able to perform atmospheric characterization of these objects. And so that's what I wanted to talk about now. And so I will take the example of these two systems, so Proxima b on the one hand and TRAPPIST-1 on the other. And I will show you the kind of atmosphere of observations that we could make on these planets to inform us, like if they have an atmosphere, and maybe also inform us about what's in this atmosphere. So I'm just going to talk now about the different kind of observations that we can make for this atmosphere of extrasolar planets. All right. The first one we can think of would be to do so here on this diagram. You can see I drew some kind of phases. So a bit like Kepler did for the phases of Venus. Actually, depending on where the planet is on the orbit, you're going to see different phases of this planet. So, for instance, if you're here, you're going to see a lot of the day side. Here you have the night side of the planet. And so this is what we call the reflection phase curve. So you see the light reflected by the planet. So here you would see a large signal, and here you would see not a very large signal, basically. You also have a thermal phase curve. So it's exactly the same principle as the reflection phase curve, but this time you're going to observe in infrared. So you're no longer going to be susceptible to the reflection coming from the star on the planet, but you're going to be sensitive to the temperature of the planet. So for instance, if you have a high difference between the day side in temperature and the night side, if the day side is very hot and the night side is very cold, then you're going to have a stronger signal. Then you can also do spectroscopy and from the reflected light and emitted light of the planet. So if you look at where the planet is the farther away from the star, it's easier this way, and then you can isolate the light coming from the planet and analyze it spectroscopically to do spectra of the atmosphere. And finally, when the planet passes in front of the star, you can see that part of the light of the star is filtering through the atmosphere, and you can also analyze it and do a transmission spectroscopy. So I'm going to talk about a bit of these, not all of them, but a bit of these in the context of Proxima and TRAPPIST-1. So I will start with the thermal phase curve. So as I said, if the key point here is that if you have a hot day side and a cold night side, then you're going to have a big signal, right? So so if you have a very hot day side and a very cold night side, it means that you have no heat redistribution from the day side to the night side. For instance, if you have a planet with no atmosphere, the day side is going to be very hot and the night side is going to be very cold, because it's going to be very efficient to cool down, let's say. If you have an atmosphere, but an atmosphere like a very thin atmosphere, then you can also have this kind of big variation between the day side emission and the night side emission. But if you have an atmosphere that is thick enough, then you can have a more efficient redistribution of the heat coming from the day side to the night side. And in that case, the curve is going to appear much flatter. And so in 2016, Martin Turbet did that exercise for Proxima b. And this is the kind of curve that he obtained. So here it's exactly the same kind of curve I showed earlier. And the dashed line corresponds to what you would have for a planet with no atmosphere. So the different colors are different wavelengths of observations. And the full lines correspond to to a planet with an atmosphere. So you can see the difference between this dashed curve and this full curve. So if we could observe that, and it could eventually be possible with the James Webb Space Telescope, which I will mention a bit later, then you could make the difference. You could potentially say if Proxima b has an atmosphere or it has not an atmosphere. And obviously, we would like Proxima b to have an atmosphere, because otherwise it's difficult to imagine that you can have liquid water on the surface and potentially life. Okay, so now let's move on to another method which is very promising, which is reflection spectroscopy. So here, in this same paper, actually, it was shown by Martin that if you take the instruments at the European Extremely Large Telescope, you can actually do this kind of reflection spectra of the planets, which is represented here. So here is the wavelength. And if you do this exercise, you can actually show that it's possible to detect water in the atmosphere of Proxima b. Of course, the planet needs to have water so we can detect it. But if it has water, it could be possible to detect it. And this was also, this has been shown to be also, this kind of observation is also possible with a combination of a sphere, which is an imaging instrument, and espresso, which is a spectrograph. And it was work done by Christophe Lovy from the University of Geneva. And so the idea of this technique is to use a sphere and so to use the technique of high contrast imaging to basically hide the light coming from the star and isolate the light coming from the planet, and then to use a spectrograph like espresso to analyze the light reflected from the planet. And so if you do that, you can potentially detect oxygen and water. And actually, this led Christophe Lovy to come up with a new instrument concept, which is called Ristretto, which is, as I said, a combination of high contrast and high spectral resolution. And so in a few years, we might be able to do this kind of observations for Proxima, for Proxima b, and potentially detect oxygen and water, which is very exciting. Then we have transmission spectroscopy. So I did not mention it, but Proxima was discovered, as I said, by the radial velocity technique. But unfortunately, Proxima does not transit in front of the star. So this observation that I'm going to mention now is not possible for Proxima, but it's going to be possible for the TRAPPIST-1 planets, because their TRAPPIST-1 planets have the good idea to transit in front of the star. And so this kind of measurement is going to be able, we are going to be able to do this kind of measurement, with the James Webb Space Telescope. So the idea really is to get the light that is going to filter through the atmosphere of the planet, and we then can analyze it. And so the James Webb Space Telescope, it's really an exciting year because it should be launched around October this year. I did not check actually if it was still the case because it's been delayed for years, but okay, I didn't check anyway. It should be launched this year, at least last time I checked. And so the James Webb is going to be able to perform this kind of observation for the TRAPPIST-1 planets. So let me go a bit more into the details of this technique, how it works. So let's imagine, so here you have the star, here you have the planet, and we are going to look at the evolution of the luminosity with time. Okay, so if you have a planet which is a pure rocky core, you're going to observe a given transit depth, which is going to depend on the size of your rocky core, let's say. But what happens if you add an atmosphere on top? So for instance, here you have an atmosphere that is going to absorb the blue radiation. So it means that this ray coming on the planet is going to be absorbed by the atmosphere. And in this part of the, outside of this region, the blue ray is going to pass. So what it means is that if you look in blue light, this planet is going to appear slightly larger than the rocky core that I drew here. So you're going to observe a transit depth that is going to be different, and that is going to depend on the wavelength at which you observe the system. And so if you add more of this atmospheric layer which absorb a different kind of wavelength, let's say, you're going to have a transit depth that is going to vary with the wavelength of observation. And so if you do observation of a planetary system at different wavelengths, you measure the transit depth at different wavelengths, then you can reconstruct the spectrum of the atmosphere of a planet. And so, for instance, here you have a spectrum that was calculated from simulations. And so here you would have the black line. Yes, but okay, but you see that there is a blue line that is slightly different. And so I'm just going to explain you what is this blue line now. And so here we have a clear atmosphere. We have an atmosphere which have several species that are going to absorb a certain radiation coming from the star. But what happens is if you have clouds now in this atmosphere? If you have clouds, what's going to happen is that the clouds are actually going to stop the certain rays of going through the atmosphere and reaching you. So in the end, what's going to happen here is that you're going to have actually the depth for the blue and green wavelength is going to be basically the same, because it's going to be let's say determined by the height at which the clouds are. And so you have these two wavelengths that are going to have the same depth. So on the spectrum of the atmosphere, you will have something rather flat. And this is exactly what we observe here in this blue curve, which correspond to a cloudy Earth-like atmosphere. And you can compare it to the cloudless Earth atmosphere. And so, for instance, these features here were features that were found from parts of the atmosphere that was lower than the cloud level. So these actually signatures are hidden due to the clouds. So the clouds, if you are a spectroscopist that wants to characterize planets, clouds are never really a good sign. You prefer good weather actually to have a better understanding of the chemical composition of the atmosphere of your planet. And so this plot was done. So here you have it was for a TRAPPIST-1 planet. So assuming an Earth-like atmosphere. And you can do the exercise with different kind of atmospheres. You can consider a 1 bar CO2 dominated atmosphere, a 10 bar CO2 dominated atmosphere, or you can even consider the atmospheric composition of the Earth in the past. For instance, here it's Archean Earth atmosphere, and you can see that you have hazes, you have clouds, and so that completely hides this kind of signatures here. Okay, so from this kind of simulated spectra, actually Thomas Fauché in 2019 showed that it would be possible with the James Webb to observe the CO2 actually in the atmosphere of TRAPPIST-1 planets. So if you are given enough time, enough observation time on this telescope, you can imagine that we can actually detect CO2. All right. So that was for the observational part. So you see that these systems are very promising because we are going to have observations of these atmospheres. But it's very important to keep in mind that these systems here are actually very different from our own solar system. They are different because the star is different. In particular, the stellar evolution of these very low mass stars is very different from the sun-like stars. But also, usually these stars are are much more active than the sun. And also, the planets are much more closer to the star than the Earth is to the sun. And so it means that they are going to be tidally evolving. And so it means that they are likely to have a very specific rotation. I'm going to get to anyway, I'm going to list all this afterwards. And they're also likely to experience an important tidal heat flux, which maybe it reminds you the slide where I mentioned the geothermal heat flux of the Earth. And so we will also see that a bit later. Okay, so let's start with the fact that these stars are very different from the sun. So here you have a plot that shows you how the luminosity of a star evolves with the age of the star. And so if you look at the black line, it's actually what's happening for a sun-like star. So the sun is here today. So it means that if you look at a few billion years ago in the lifetime of the solar system, the sun was actually a bit fainter than it is today. But if you look at lower mass stars, and particularly, for instance, this one, 0.08 solar mass, you can see that if you are here today, then a few gigayears in the past, you were actually more luminous. The star was more luminous. And together with the fact that these stars are active, so here, for instance, you have a spectrum of these stars compared to a spectrum of the sun. So here on this plot, it's comparing the flux coming from Proxima and the flux arriving on Proxima b to the flux arriving on Earth. So the Earth is in red, and so you can see that most of the radiation coming from the sun is invisible. Here, the sun this time is not in red; it's in blue, but you can see the same thing. And so here you have the light coming to Proxima b. And what's very important here is that on this side of the spectrum, so on the more energetic side, so where you have the UVs, where you have the X-rays, etc., you have an emission which is much more important for Proxima and TRAPPIST-1. So it means that before arriving in the habitable zone, the planets actually were too hot to sustain surface liquid water. So all the water was in the atmosphere. And so depending on what happens to this water, if the planet at some point reaches the habitable zone, because the star is being less and less luminous, and so the habitable zone comes closer in. So for instance, if you lose all the water, for instance, you would have a planet like Venus completely desiccated. But if somehow the water loss process is not that efficient, you could have retained some water and be habitable Yeah. So this topic was extensively studied by a lot of groups, and I would just like to go a bit more into the details on what's happening. And so it's going to be very, very similar to what I said in the beginning with the most greenhouse effects, because actually the beginning is exactly the same story. So you have an extended atmosphere, you break the water molecules in the upper atmosphere, and then the XUV drives the escape of these atoms. And actually what's happening now is that once you arrive in the habitable zone, so once the star has cooled down, so once the planet is able to have temperate surface conditions, you can actually recombine the oxygen molecules and dioxygen in your atmosphere. And the atmosphere is no longer to be that extended. It's going to be less extended. And because you are in the habitable zone and the definition is that you can have surface liquid water, then the water in the atmosphere can condense and form lakes or oceans. So the outcome of that is that you have less water than in the beginning, and you also have an oxygen excess in the atmosphere. So this kind of calculation, so trying to estimate how much water the planet loses has been done for Proxima and TRAPPIST-1. So for Proxima, it has been shown that it could be less than 2 Earth oceans or up to 5 Earth oceans, depending on the model, depending on the many assumptions that are hidden in this kind of model. This is what the estimates were found to be. So it seems like it's a lot, but if you remember that actually you can form planetary bodies with way much water than the Earth, maybe 2 or 5 Earth oceans is not that much in a large context of planetary formation. So all in all, Proxima b could have retained some water. And so with Strator, for instance, we will be able to see if that's the case. Then for TRAPPIST-1, so the B and C planets are very close into the star. They are never going to reach the habitable zone. And so they are losing water basically all the time. And so depending on the age of your system and all these hypotheses of this kind of model, you can find that this very close-in planet could have lost up to 100 Earth oceans. But very good for us is that these models also show that for the planets which are in the habitable zone, so E, F, and G, they actually lose a little amount of water. So it means that if they were formed with sufficient amount of water, it's highly probable that they have retained some of it now. So that's a good sign, let's say. And now I would like to focus a bit on the fact, because I passed very quickly on that aspect, but it's very important. The fact that this process of losing the water actually has the consequence of the thing that you can have an oxygen excess in the atmosphere of your planet. So it means that you can observe a planet in the habitable zone with oxygen in the atmosphere. And if you are familiar with our planet, you know that actually on our planet, oxygen is a gas that is present in the atmosphere due to the processes of life. So it's often that oxygen is actually proposed as a biosignature. So a biosignature is a signature of life. And so, given the example of Earth, we could propose oxygen to be a biosignature. But what I've just shown you earlier, meaning that the process of losing water during this initial history of these planetary systems around very low mass stars, really has the impact of creating oxygen atmospheres rich in oxygen. So it means that for these planets around low mass stars, you have a process that is purely abiotic, that has nothing to do with life processes, that can create this signature of oxygen. So a planet, so it really illustrates, and it's a very important point, that it is very difficult to identify good biosignatures, because for a given signature, you can have actually a lot of processes that could have, that could actually also create this gas in the atmosphere of the planet. So it's very important to try to understand the context of the planet. Did it, have this very hot early history in the system that drove this evaporation of water? And this might explain this oxygen that we are seeing now, and maybe it's not life. So you see, you really have to keep that in mind, and the claims of biosignatures would have to be very careful, because you have to really understand the context of your planet to claim a biosignature. Okay, so now let's move on to the second part on the star, which was the fact that these stars are actually very active, and I showed you earlier. They have a high UV and X-ray radiation compared to the sun. So here is another plot showing that. So here you have basically an activity indicator, and here you have the type of the star, with the sun here. And if you go on the right, you go to the lower and lower mass stars. And you can see that this activity indicator is actually going up while the stellar mass is going down. So M dwarfs are much more active than sun-like stars. So this can be a problem, and this can also be a good thing, depending on if you are optimistic or not. So here is another plot. So here it's slightly different. It shows you, okay, so when a star is active, it can have flares. So you can eject energetic particles around in an interstellar medium. And so here you have the flare rate, meaning that if you are here, you have flares happening like super frequently. If you are down there, flares are quite rare. And here you have the energy of the flare. So here you have a low energy flare, and here you have very high energy flares. And all these points are observations from these M dwarfs, so from these low mass stars. And here you have shaded areas, red and green. So if you are in the red one, it was shown by Tilly in 2017 that if you are here, the flares are frequent enough and strong enough also that if you have an ozone layer on the planet, it's going to be destroyed by the UV radiation. And the ozone layer obviously is important, and we know it on Earth because it protects us from these UV radiations. And so if you kill that protection, the surface is going to be bombarded by UV radiation. And so the idea is that this bombardment by UV is going to destroy complex molecules. And so it's going to be much harder to create complex molecules that are needed for life. But at the same time, something that was illustrated by Rimmer et al. in 2019, 18, sorry, is that you need also some flares because you have to have some of these high energy radiations to trigger the prebiotic chemistry. So basically, it's a very delicate balance, and it's not clear of all these systems which are good. So here, for instance, there is one point in a green region that could be a good candidate. But it's also something to keep in mind. It's not, even if you are in the habitable zone, these environments can actually be very hostile because of these high energy radiations. Oops. All right, so now let's move on to the last part of this lecture. So the fact that these planets are also much closer to their star. So as I said, they are going to be submitted to tidal evolution. And one of the outcomes, which is particularly interesting for us here, is that tides are going to impact the rotation of these planets. So that if you have a planet that is rotating at a given rate at some point, then tides are going to act to synchronize the rotation of these planets. So it means that the rotation frequency of the planet is going to be the same as the orbital frequency. And so that means for us, what's interesting is that it means that the planet is going to have a permanent night side and a permanent day side. And that can be actually dangerous for the habitability of the planet, because if you are very, very cold on the night side, you can actually condense all the water and even some species of your atmosphere, like the CO2. And if you are very, 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 very cold, you can also collapse your entire atmosphere. So this configuration might be challenging for habitability as we know it. But if you have an atmosphere that is thick enough, you can actually find good habitable conditions for these planets. And so that's another work of Martin Turbet in 2016. What he did is that he took global climate models. So here is for Proxima b. So it means that it's 3D models of the atmosphere. So you consider no longer a single column of the atmosphere, but you consider the whole atmosphere and the dynamics inside, the radiative transfer in the atmosphere, everything. And you do some assumptions. So for instance, here it's a planet that has a lot of water. You do assumptions on the composition of the atmosphere, for instance, with CO2, nitrogen, etc. And then you make this model run, and this is one of the outcomes you can get for this synchronously rotating planet or tidally locked. So here I'm going to pause. So here you have the substellar point. So the day side is over here. You have high temperatures, and on the night side you have very low temperatures. And here this dashed line represents you so if you are inside this line, basically you have liquid water, and if you're outside here you have ice. So here you have an example of a synchronous rotating planet which has an ocean on the day side. And if you do an image, if you illustrate what this kind of planet could look like, this is what you would have. They are also called eyeball planets. So you have a substellar point ocean, and you have ice on the night side. So this kind of climate, so as I said, the previous simulation was for Proxima b, but this could also be the case for TRAPPIST-1e, for instance. So maybe I'm not going to mention that, but if you have an eccentric orbit, you're going to have a different kind of rotation, and so you're going to have a different kind of climate, etc. But I'm not going to go into the details. Here, I just wanted to mention. So here, I gave you one example of climate. If you have a lot, of water at the surface of the planet and a given amount of CO2, and here this plot show you how this climate could evolve if you change here in the y-axis the amount of CO2 on your planet, and here the amount of water on the planet. So basically, where you have colors, you can have a climate that allows, in some conditions, some liquid water to be on the surface. And so for the synchronous rotation and a non-synchronous rotation. And so here, for instance, you see this yellow-orange line. It tells you where, if you are below this line, actually, you can condense even the CO2. So it reminds you of this cold trap idea I mentioned a few slides earlier. Okay, but all in all, if you look at the whole parameter space, it looks like for this kind of planets, and so here is for Proxima b, but it's also true for TRAPPIST-1e, for instance, then you would have a lot of parameters, like sets of parameters that could actually be compatible with surface liquid water. Okay, so and finally, I wanted to also mention a thing about the geothermal heating for these planets. And to do that, I'm going to do the analogy of the TRAPPIST-1 planetary system with the Jovian system. So here you can see that the TRAPPIST-1 star, represented here, is very close in size to Jupiter. But of course, in mass, this object is way more massive than Jupiter. And in terms of the orbital period of the satellites of Jupiter, they are also kind of similar to the orbital periods of the planets of TRAPPIST-1. So we have a big similarity between the two systems. And we know that in the Jovian system, and in particular for Io, due to the fact that Io is a constant, the eccentricity of the orbit of Io is constantly being excited by the other satellite. The satellite is actually being constantly deformed due to these tidal interactions. And this constant deformation creates heat in the interior of the satellite that wants to get out. So here, for instance, you have a super huge volcano at the surface of Io. And here, I really like this image. So it's an image in infrared from Juno. So here you have the day side of the satellite, and here on the night side, you can see all these bright spots in infrared. So it means that these are what we call a hot spot. It means that it's a signature of this heat that is inside the satellite that wants to get out. So on Io, you have a strong volcanism. And actually, for the planets of TRAPPIST-1, they also experience this tidal heat flux. So it's probably very intense for the very close-in planets. So for instance, B and C could actually have a magma ocean on the surface because the tidal heat flux is so intense. And for the planets in the habitable zone, this tidal heat flux is more or less like the heat flux coming from the Earth, which is not mainly due to tides, it's due to the radioactive decay and such. But we could imagine then, if these planets have the same kind of geothermal activity, let's say, that the Earth, they could have volcanism and also degassing. And also this could induce a magnetic field, in the molten parts of the planet that could protect the atmosphere of the planet. But also, very interestingly, we could imagine that the geothermal activity is enough to have this kind of black smokers or similar geothermal structures in the potential oceans of these planets. And so you could have conditions that are very similar in the end to the early Earth, to the conditions of the early Earth where we think life might have appeared. All right, so I will conclude. I was a bit longer than I expected. So we saw together that the definition of the habitable zone, which is a very important concept in the community. I hope also I showed you the limits. I mean, this definition of the habitable zone really relies on the assumptions that we use to define them. And to detect a planet in the habitable zone does not tell you that the planet 100% for sure has surface liquid water. Then we talked about the small star opportunity, so saying that there are a lot of these small stars and the planets are easier to detect around them. That these planets, using climate simulations, we have seen that these planets can host surface liquid water for a wide variety of atmospheric compositions. And very interestingly, we have seen that in a near future and very near with the James Webb and a bit farther away with Ristretto on the ELT, but we are going to be able to characterize the atmosphere of these planets to say, okay, if they have an atmosphere, and maybe tell one or two ingredients of these atmospheres. And so also one key message is to say that we need actually to understand the context and the history of these planetary systems. And so we really need an interdisciplinary approach of planetology to be able to correctly interpret these future observations, and especially in the sense of biosignatures. And with the example of oxygen, I showed you that you can have a purely abiotic process that has, the effect of having this O2 in the atmosphere of these small planets. And with that, I will thank you, and I will be happy to answer any questions that you might have.